I'll give the proceedings to host, and you can go. And I
Yeah.
welcome the members who are not a member yet. They should join ASM International India chapter and reap the benefits of our activities. Thank you. Thank you very much.
Hello. Good evening, all. Can you
Yes,
hear,
yes.
Vivek ji? Yeah. So let me briefly introduce Dr. Osmani. He did BE in Metallurgical Engineering from NIT Nagpur and MTech from Bombay IIT. He was the recipient of DAD scholarship for doing MTech research at Stuttgart, Germany. He got his PhD degree from University of Stuttgart in 2006. Completed his PhD in the area of nitriding of iron-based alloys. He continued in research after PhD as a postdoctoral scientist for about 3 years in Germany, Stuttgart, and USA, Cleveland, Ohio. He held the regular faculty positions at NIT Surathkal, IIT Delhi, and COE Pune. He gained an industrial experience as a senior manager at R&D Center of Bharat Forge Limited, Pune. Currently, he is an associate professor at IIT Indore. He has several publications in international, national journals and conferences. He has written a book on an introduction to surface alloying of metals. He is also a co-author of one book chapter that is published by CRC Press in 2016. He has guided 9 BTech, 19 MTech, and 1 PhD thesis. The research interests of Dr. Osmani's group are surface engineering, tribology, and physical metallurgy. I welcome Professor Santosh Osmani and to start the boronizing of steel. Thank you very much, all the members, and let us listen to Dr. Osmani.
Rege,
Welcome, sir.
if may I add one line?
Yes, sir. You have all the.
Dr. Osmani was also part of our flagship event MET STS as a speaker.
Yeah. Yeah, in 2018, right?
Yes. And he
so he
joined us
continued.
for the next event.
So
Yes.
request him.
Yeah, 2020.
You can request him for this our coming event.
Yes, already done that.
Yes. That was done. Yeah. Thank you. So, Dr. Osmani, we are keen to listen to you now.
Yeah, definitely. Thank you, sir. Thank you very much.
Yeah.
So then I will
Welcome,
share my screen. Yeah, so I think my screen is visible to everyone, I guess.
Yes, doctor.
Yes, it is.
Good.
Yeah, thank you very much for the kind introduction. So it's really my pleasure to be here and to give a talk on the heat treatment related topic, and which generally I used to work in this area for quite long, since my PhD actually. In fact, not PhD, in fact, my master thesis also. So I did my master thesis in nitriding, then subsequently continued with the PhD postdoc in the same area. And then onwards, after returning back to India also, I'm mostly working in this surface engineering related activities. So now I would like to, first of all, thank you very much for giving me opportunity. And I really appreciate the efforts made by the ASM International India chapter for various activities, because when I was in COP, I used to see a lot of activities, a lot of talks which are being organized by ASM International. And it's really a pleasure that you guys are really working hard to bring the closer between, or to close the gap between the industry and academy. So that is the most important challenge currently, all of, especially in organizations like many academic institutes they are facing. So I really appreciate this effort. Now, without delaying, I will start straight away with the topic. And my topic title is Boronizing of Steel. So you're already aware that the surface engineering is very much required for various applications. And you know that why that is required, because the requirement from the bulk and surface, they're different. For example, you take an example of a turbine blade, or you can take example of a gear. So there actually a bulk of the material need to have a properties like it should be tough, it should be shock resistance, and as well as it should be able to deform. Then weldability should be there, machinability should be there. So all those requirements will be there from the bulk material. However, the surface has to do a different job. So that means the surface has to protect the material from wear and tear, as well as the hostile environment like oxidizing environment or even the humid environment. So that means corrosion and oxidation resistance is also another criteria surface has to meet. So many times, if that is the case, we have one option that we can develop a material or the alloy which can fulfill the both requirements. That means the requirements of the bulk properties as well as the surface properties. But many times it's not really very easy to have the properties whatever we're looking for. At the same time, it may not be economical as well. So instead of that, we can start with very cheaper material, and then we can find out the way to change the surface property. So that is why the surface engineering is becoming very popular, especially nowadays. So now you know that there are various types of surface engineering techniques are there. And one broadly classification is that we can change the surface microstructure with respect to chemistry as well as without chemistry. That is one approach. That is we call as a surface treatment. And there is another approach where we deposit the nobler material over the surface that we call as a coating technique. So the current talk is basically related to the surface treatment, where we are going to change the surface chemistry by introducing the boron into the surface. So now, basically the boronizing technique is quite old, and this was first proposed. The idea of this boronizing was proposed back in 1895, along with the nitriding and carburizing. And since then, the science behind this particular process was slowly got the sufficient understanding. And by the end of 1967, so there was enough understanding about this particular process was there. And subsequently, there are many literatures even till today being published in this particular area. However, the first book on boronizing of steel was published back in 1978. And since then, we have plenty of literature are available in this particular area. Now, as similar to the carburizing and as well as the nitriding, boronizing can also be done by various ways. One option is that we can use a solid medium, and there, due to the high elevated temperature, some reactions will occur, and that reaction will basically generate the boronizing potential there. And that boronizing potential will be useful to introduce boron into the steel surface. Not only just steel, but it can even the non-ferrous material. That is one approach there. And the solid media that is called as also the powder pack boronizing process, and which is a very popular because of its low cost. And other options which are available like a liquid media is also there, but some of the environmental issues are associated with that. And then the gaseous media is also being used to have the boronizing. And other techniques like even laser, plasma, even ion implantation, glow discharge. So all those techniques are also available. People have explored that, and successful boronizing has been achieved. However, pack boronizing is quite popular, and various industries, they're basically there in boronizing business. These business can be associated with the supply of raw material, or some industries that even give the boronizing of the various components. So like, for example, from India, there are few companies are there, and as well as across the globe also, there are various companies they're actually involved in this boronizing business. Now, you must be wondering what are the materials which can be basically boronized. In principle, you can boronize the ferrous alloys as well as the non-ferrous alloys. So in ferrous alloys, basically all types of steels, even the cast irons can also be boronized. People have successfully done that. And in case of a non-ferrous material, nickel-based super alloys are also boronized successfully, and as well as the cobalt-based alloys and titanium alloys. Then the application point of view, there are various components are there. Mostly these components are associated with the agricultural harvesting related components, even the oil and gas industry related components, even the blades, cutters, even the cutting tools, even the dyes, extrusion dyes. So that means the plenty of components can actually be subjected to the boronizing. And these are the few of these components just for your imagination. And here you can see that these components are successfully boronized as the claimed by the various companies which are actually mentioned here. And you can see that here the impeller, diffuser, even agriculture harvesting components, and as well as the boronized oil well tubing, and as well as the drilling tools. So those things are also people have successfully boronized, and people are using this technology widely. In fact, the vapor coat, so that industry has claimed that boronizing is a perfect solution. Especially why that is so, because it basically helps to limit the wear and tear wherever the friction related things are there, and as well as it has a very good resistivity to the soil acidity, and it actually stops the redox reaction at the metal surface. So that's why the boronizing surface is quite suitable for that purpose. And here, just for the comparison of the boronized steel along with the other options which are available, like for example, tungsten carbide, that can also be there, as well as the nitriding option is there, chrome plating, carburizing. So here you can see that the boronized steel has extremely good hardness. So that's why this particular technology is very much being lucrative with respect to even probably it may even the outperform the nitriding and the carburizing related options probably in near future. Good thing is that whatever the boronized layer which form on the steel surface, so that will not be immediately detached from the surface, even though that is very hard, but it will not be detached immediately. So that is associated with some of the properties which are linked with that particular material, which I briefly explained during the presentation. Now the boronizing, as you have already guessed, so this is basically the thermochemical treatment, and it is basically driven by the temperature, and ultimately we need to have some kind of a boron source there, and that boron source will introduce the sufficient boronizing potential, and then the boron will be introduced. Now fundamentally we need to understand the iron boron phase diagram, and unlike the iron carbon and iron nitrogen phase diagram, the iron boron phase diagram looks entirely different. So here we see that in case of the iron nitrogen and iron carbon system, you have the sufficient solubility for nitrogen and carbon in austenite. But that is not the case in case of a boron. If you see the solubility of boron in ferrite as well as austenite, it is extremely poor. However, there is a possibility of formation of the iron borides. And two types of iron borides are generally formed. That is, one is Fe-B and Fe2B. And from the composition itself and stoichiometry, you must have guessed that the Fe-B layer will form at the top. And then subsequently, there will be the Fe2B layer will be there. And then you have the non-boronized core will be there. Now, what are the properties which we need to understand? Because always there is a question whether it is better to have a single boride or single phase boride layer, or we can have the two-phase boride layer. To answer that, you need to understand especially the properties, that is the physical properties associated with this. With respect to composition, whenever the boron content in steel, it exceeds beyond roughly 9 weight%, there will be the formation of Fe2B phase will form. And whenever the concentration of boron exceeds about the 16 weight%, there will be the formation of Fe-B layer. And if you see the crystal structure, so basically Fe2B is having the BCT structure, that is a tetragonal structure, and Fe-B is having the orthorhombic structure. And their lattice parameters are entirely different than the lattice parameter of ferrite as well as austenite. And if you know that basically the lattice parameter for the ferrite is roughly 0.28 micron, or in case of angstrom, it will be 0.8. And in case of the FCC, it will be about roughly 3.5 something. So if you compare these lattice parameter with respect to these Fe2B and Fe-B, they are entirely different. But still, this layer is quite intact during the formation process. And if you see the density-wise, so density-wise, Fe2B is denser compared to that of Fe-B. And hardness-wise, both are having almost same hardness, roughly about the 20 GPa hardness. And Young's modulus is significantly different. And Fe-B is quite stiff compared to that of a Fe2B. That is also one of the criteria you can imagine why there should not be the two layers together. That is, stiffness is the one issue. And the second important issue is basically coefficient of thermal expansion. And if you see that, the coefficient of thermal expansion of both the borides is entirely different. That is also a critical issue. And because of that, there is a possibility that formation of Fe-B layer on the Fe2B layer probably will not have that much adherence to the surface. And many times it is a desire that you should not have the Fe-B layer, better to have only Fe2B layer. Fortunately, the Fe-B layer is quite thin compared to that of a Fe2B layer. That is so that is why, even though any kind of a disadvantage associated with the Fe-B is there, by using a machining or even during the process, you can even offer to have a little bit of Fe-B there. Okay, so now another fundamental thing is that we need to understand the diffusion or the migration of boron in the both types of a lattice, whether the open structure, the BCC structure, or you can have the closed pack FCC structure. It is austenite structure. Here you can see that similar to that of a diffusion of the carbon and nitrogen in ferrite and austenite, the diffusivity of the boron in ferrite is relatively faster compared to that of in austenite at a particular temperature. And that is why, because we have the activation energy barrier for the diffusion or migration is quite high for the FCC matrix compared to that of the BCC matrix. And that is quite well or matching with the phenomena associated with the carbon and nitrogen diffusion. Actually, originally, this diffusion concept was introduced in 1953. However, that equation was having some error, and then later on that was corrected. And in 1995, whatever the equation which is mentioned on the screen is actually proposed, and still people are using this particular expression. And important, what you can notice here is that as the temperature increases, especially beyond the 600 degrees Celsius, actually diffusivity is not really much different in ferrite matrix as well as the austenite matrix. So that means, in principle, unlike the carburizing process, so there is no such a requirement that you need to be in austenitic phase region. Because in case of a carburizing, we require that we need to be in austenitic phase region because we have the very high solubility of the carbon there in austenite. But here, that is not the criteria. We have seen in just in phase diagram that solubility is not really great in both the phases. So that is not the criteria. Only advantage what you will get at high temperatures is that diffusion will be faster anyhow, and your process will finish early. That is the only advantage we can get. Otherwise, the phase point of view and solubility point of view, we don't have much requirement that we should be in austenitic phase region or something. So people have successfully boronized even at 800 degrees Celsius. Also, they have boronized even pure iron. They have successfully boronized. So that is what actually we have. Only criteria is that a high temperature actually helps us to have the effective chemical reaction which are happening at the surface, because the chemical reactions, they are also having their own activation energy barrier. So high temperature will definitely helps us to overcome that barrier, and your chemical reaction rate will be faster. So that advantage you will get due to the high temperature along with the high diffusivity. Okay, so now I will talk about the pack boronizing method, which is the most economical method. So what are the basically content in that particular powders? Basically, there are three types of powders are there in that mixture, powder mixture. One is basically boron source, and the second one is the activators, and the third one is diluent. So boron source, there are a wide range of boron source are available. People have even mixed the amorphous boron, even the crystalline boron, even they have mixed with the borax, even the ferroboron. But Fe4B is widely used by the commercial powders which are available there. So B4C is basically the boron carbide is widely used, and activators mostly KBF4. So that basically the halide type of the compound is generally used for the activators. And dilute, in principle, the role of a diluent is just to provide an inert atmosphere so that whatever the environment is generated, that will be pretty uniform surrounding the specimen surface. So that will be the role played by the diluent. And mostly people use the SiC as a diluent. This SiC considered to be the inert at a boronizing temperature. However, what actually literature observed, and also we also observed in our work, that especially at elevated temperature, that SiC actually forms a sticky layer on the surface, on a steel surface. And that sticky layer is difficult to be removed easily. That means probably you have to do some kind of the grid blasting or something to remove that sticky layer. And probably that may add some additional cost. So that could be there whenever you're using a very high temperature, especially beyond 1000 degrees Celsius. Otherwise, this SiC has no role in any reaction as such. Then the process temperature, as I mentioned, in principle, you can go even as low as 800 or 850 degrees Celsius and as high as 1100 degrees Celsius in principle. And the duration, it will vary from whatever the thickness you are looking for. And people generally use the range from 2 to 24 hours. Now, of course, 24 hours is a too large duration, and many times it's not required. Even 6 hours or even 4 hours is pretty good enough to get a layer thickness in a micron. So that advantage is there, especially in boronizing process. Now the commercial suppliers. So there are various commercial suppliers are there. For example, Icabor is that is a German supplier, and they are supplying this particular boronizing powders. And they are not revealed the composition, but it is believed that most of the commercial powders, they are having about 5% of the boron source. You can say about the B4C, that boron carbide can be there, and 5% of activator will be there, and 90% will be the SiC. Most of the commercial commercial supply. Of course, they have not revealed this composition, but it is believed that this the possible composition these powders must be having. So now the experimental setup. So experimental setup is a pretty simple. You have the container, and the material for container ideally is the steel container. Even you can go with the mild steel container, even the stainless steel container people widely use. And then in that container, you must adopt a particular mixing process. So that means whatever the layer thickness you are putting, that is boronizing mixture, then followed by the alumina powder, or even the glass powder. So whatever the combination you are selecting, that should be uniform throughout your process. Otherwise, it's very difficult to control the boroid layer thickness, and you really cannot predict what will be the scenario in pack boronizing. So you need to adopt a particular sequence. So what actually we used to do for in our container, we have about the 20 millimeter layer will be deposited by the this boronizing mixture, and we keep the sample over it. And then again, we have a 20 millimeter layer of this boron powder is there, and then followed by we use the alumina powder, even the silica is there, as well as even glass powder. So that is basically purpose is that to avoid any kind of environmental contact with the boronizing mixture. Because the problem is that if you have the oxygen trapped into this powder, that will lead to the formation of porosities at the specimen surface. And that will again create a problem, especially during application, because if the porous layer is their top layer, either you have to remove that porous layer or you have to find out the way to close those pores. If that is not there, in principle, that will be the disadvantages, because you can have the cracking can occur easily, especially the top layer. So that's why people have used the various combinations, and even people use in furnace, they have used the inert atmosphere also. So probably inert atmosphere will take care of to eliminate the oxygen which is there in the environment, and you can avoid the unwanted reactions there. The major reaction which is there in this container is basically the reaction between the boron source, that is a B4C, and it is believed that in that boron source you have some boron oxides are also there. And these boron oxides are playing a role as an activator. And the reaction between the boron source and this boron oxide, that will lead to a formation of a boron oxide having a different stoichiometry. And as well as that stoichiometry has a lower stability. That means there is a possibility that that oxide will again go back to its original oxide form, leaving behind the boron in the atmosphere. And that boron will be the adsorbed boron, and then it will be reacted with the metal surface, and there is a formation of metal borate. So that is what actually mechanism people have proposed. Another possibility is that there is a formation of the boron halides. These are the gases, and these boron halides will reacting with the metal surface, and then they ultimately form the different stoichiometry of boron halide, and then you have an adsorption of the boron and formation of compound. So that is another mechanism people have proposed. Now, if you look at this, the right side diagram, you can see that people have used different combinations, and basically they use electric heating type of a furnace there, and your combination can be different depending upon what type of a quality of surface you are looking for. So you can fill that chamber with inert atmosphere, even vacuum, you can do that. Even your container can be a longer container, only limited portion of that container is exposed to the elevated temperature. That means even you have like a shaft type of a component, and only limited region of that particular shaft you want to have boronizing. So that is also possible, because only heated region should be exposed there, because chemical reactions will occur wherever the temperature is sufficiently high. Then only boron potential will be generated. Otherwise, it will not be generated. That means selected region also can be successfully boronized in this particular pack method. Only thing is that you have to just alter with the design. So now basically there are well-known 5 to 6 steps are there in this boronizing process in physicochemical model. You have the free boron, which is coming from the atmosphere, and this boron potential is depend on a lot of factors. One is the chemistry or composition of your boron mixture, and as well as the temperature is there. Then there is adsorption of boron will be there, and that adsorbed boron will react and form the Fe and Fe2b. Now again, formation of Fe and Fe2b depends upon the capability of the atmosphere. If the boron potential is high, then only there will be the formation of Fe. Otherwise, it will not be lead to the formation of Fe. You have only Fe2b. Then there is the migration of this boron will be there across the interface of boron and compound layer. And then finally, these boroids will grow. Now the growth is also that morphology of, again, depends on this particular crystal structure of this boroids that I will discuss later. And then the growth of this boroid will happen there. And as you know, there will be initially, there is a formation of Fe2b will be there. And then subsequently at latter stage of boronizing at the surface, there will be the consumption of Fe2b will happen, and that will lead to the formation of Feb. obviously system wants to grow both layers together. That means FEB layer will grow together with the growth of FEB layer, FEB and Fe2B layer. That means at the surface, to achieve the equilibrium between these two compounds, there is a possibility that there will be have some kind of a dissolution of FEB to Fe2B, or vice versa, Fe2B into FEB. So those reactions can occur at the surface during the growth. And this is the simple mechanism what actually people have proposed, and this is from our work. And actually what actually happens initially there is a formation of a compound which is a boron rich compound, and that compound is neither FEB nor Fe2B. It is just a boron rich compound, and then there is a nucleation of Fe2B will happen there, and then it will grow as a sawtooth morphology. Again, that morphology depends upon the again, it depends on the composition of a steel. If you have the low alloy steel, then you have, or the medium alloy steel, most of the time you have a sawtooth morphology of these borides people have observed. However, as you keep on increasing the concentration of alloying element, your morphology will change. It will become a more smooth morphology than the sawtooth morphology. That I will discuss later, because that is also an interesting aspect we need to understand. And then subsequently, what happens, you can see that there is some transition zone is shown here. What exactly is transition zone? Actually, whatever the alloying elements which are present in steel, all elements will not be accommodated into iron boride. Some elements have limited solubility in iron boride. Some elements do not have any solubility at all. That means they will entirely rejected by the these borides, and they will accumulate at the front of these borides, and that will form a transition zone. And many times that transition zone will alter the mechanical property, and that alteration may be disadvantageous. So that transition zone concept also we need to understand. That also we will discuss later. And then finally, you have a simultaneously growth of these three important layers. That is a transition zone, as well as Fe2B, and then FEB. That is what actually we have the typical cross section. Now this particular sawtooth morphology, why that sawtooth morphology is observed? What people propose, the idea is that basically this Fe2B is having a tetragonal structure, and actually boron diffusion is generally preferring to migrate, or the boride prefer to migrate along the 001 direction by stacking the planes of 100 and as well as a 110. So these planes will be stacked in a direction of a 001, and because of that, we are getting the sawtooth type of a morphology basically is observed in most of the case of a steel. So that is what actually is mentioned there. Now, as I mentioned previously, why we don't want to have two layers together. So here is the one example here. Here actually they have studied the ASI 304 steel, and you can see that clearly at the microstructure. There is a formation of Fe2B is there, as well as FEB is there. And that formation, and you look at the nano indentation study where they mention the hardness profile and as well as the residual stress profile. And here you can see the figure number E, that residual stress profile, and that residual stress profile, I will just use a laser pointer. Yeah. So in residual stress profile, you can see that. So here you have basically the tensile nature is there, especially in FEB layer, that is the top layer. So top layer FEB is having a tensile nature, and Fe2B is having a compressive residual stress. So now you have this tensile nature is definitely not desired. You know that. Because that can easily initiate the cracking. And as well as these two layers are having a different crystal structure, coefficient of thermal expansion is also different, and most likely there will be very weak adhesion between the FEB and Fe2B layer. And that means there is a possibility that that FEB will be detached during operation. So that possibility is most likely there. And apart from that, the nature of this stress is very much dependent on your process parameter. So here actually they have studied at a constant temperature at a different time. You can see that initially whenever temperature was quite less, it was 2 hours. In that case, you are the FEB layer also, it is having a almost like a compressive residual stress. To some compressive residual stress is there. However, as the time progresses to 10 hours, that residual stress nature is actually changed from the compressive to tensile in nature. And that is actually happening because of the growth of this boroid layer is happening. There's a difference in their crystal structure is there. And ultimately that will enable to withstand that particular stress which are generated simultaneously in FEB and Fe2B layer. Because the properties of this FEB and Fe2B layer, that is depend on the elastic strain. That means the capability of that particular boroid layer to accommodate the elastic strain, which is generated due to the residual stress mismatch. because whenever there is a formation of Fe2B layer on the substrate, which will be the ferritic or austenitic during the boronizing, so that lattice parameter difference is there. But Fe2B is having some flexibility, and as well as the elastic strain is sufficiently high there. And because of that, whatever the mismatch is there, your system is able to accommodate. So that's why very good adhesion of this Fe2B layer is observed, especially in case of a boronized steel. Now, another important aspect is the composition of the ferrous alloy. Actually, this is very complicated concept of behavior, especially in case of a boronizing, which is the least understood actually. During boronizing of these ferrous alloys, various compounds, various elements, they have a different response. For example, the elements like chromium, aluminum, silicon, these elements restrict the boroid growth. However, the elements like cobalt, nickel, manganese, they don't have much effect on restricting the boroid growth. However, this restriction, whatever is shown here, this is basically associated with mostly the binary system. But in reality, whenever you have the presence of multiple components, the behavior of this element will be entirely complicated, and probably it may not be behave what actually shown on this particular screen. But broadly speaking, the carbon, silicon, aluminum, chromium, they restrict the boroid growth, and manganese, cobalt, nickel, they don't have much effect on the growth of boroid. Another interesting thing is that if you go through the literature, so you realize that different morphologies of these iron borides are actually shown by different authors. And here you can see on the screen the figure number A to C. So these are related to the steels which are having the concentration less than 5%. That is, concentration of alloying element is less than 5%. Then you go to the figure number D, which is having the concentration, D and E, they're having a concentration about 17 weight%, and F is having very high concentration, greater than 30 weight%. And you notice especially that in case of the low alloy steels, the morphology is more or less like a sawtooth morphology. However, as you go to the medium or the high carbon, high alloy steel range, having about 17% range, you can see the FeB and Fe2B, you can see from the color contrast, FeB appears like a darker as compared to that of Fe2B, so that you can distinguish that. And you look at the morphology of a Fe2B, it is the morphology is more or less smooth. It is not really appearing like a sawtooth as such. Some sawtooth appearance is there, but it is not as sharp as that of a low alloy steel. But your FeB morphology is still like a very sharp sawtooth morphology. Now, interestingly, as you go to the figure number F, which is having a very high concentration, and you can see the different layers there. You can see the transition zone layer. You can clearly see the FeB layer, which is the darker in nature. Then you can see the Fe2B layer, which is slightly whitish in nature. And you can see the interface between these, that is the interface between Fe2B and transition zone, and as well as FeB and Fe2B. It is a quite smooth in nature. That means the morphology of these borides is significantly dependent on the concentration of this alloying element, apart from the effect of alloying element on the migration behavior of these borides. So along with that, these two important effects are basically leading to in governing the morphology of these iron borides. And that is ultimately very important, especially with respect to the mechanical properties of this particular layer also. So that I will quickly discuss. That means we need to understand this, especially the microstructural aspect and the role of these alloying elements during the growth of these borides. And that was our main motivation for the study. So what actually we studied here? So actually we started working on this particular topic in 2013, and we extensively did a lot of experiments. So we did with the container as well as the boronizing parameters like temperature, time, everything. And we got some of the interesting results there. So that we will show initially. And then we will slowly migrate to the more scientific aspects related to the migration of the alloying element. That was the typically very complicated aspect, which actually we proposed during our study. And then finally, we talk about the mechanical aspects using the various techniques, including the oxidation and as well as the wear. And then finally, whatever the lacunas which are associated with the boronizing, how we can tackle that by using the duplex treatment, like a post-treatment. So that actually we will discuss quickly. So now the pack boronizing process optimization has been done, and in process optimization, I will show basically the two types of steels we have used. One is ASI 4140 and the EN41B steel. And we have performed the experiments at a different. So it's Basically, our main intention is that, first of all, these two steels have wide applications, and as well as these elements concentration is quite less in this particular steel. And we want to understand this particular material more into depth. So that's why we selected these two alloys here. And these are basically literatures we'll find in this particular topic. And here, actually, what I mentioned earlier, so we use initially 3 different types of containers there. That is a small container, medium sized container, and large container. So I mentioned that you are using a material container is a steel. It can be stainless steel or even a mild steel. You have to remember that during boronizing, your container will also consume the boron potential, which is generated. And that you have to, most of the time, you have to take care of that. And that's why people used to have the pre-treatment of the container itself first, so that the consumption of the boron potential by the container will be minimum. However, some consumption will always be there. And here you can see the effect. In case of a small container, where boron potential will definitely limited because quantity of powder is less there. And in this case, we have not found any kind of a boroid layer as such. This layer is something like a more or less dominated by the sticky layer, which is a form there. And there is no as such boroid layer in case of figure number A. In case of a figure number B, we have about the 2 hours. Temperature is same in all cases. There we have seen the compound layer formation. And by using the EDS chemical analysis, it shows that we have very high boron as well as a carbon content there. That rich content is there. And the hardness value is very slight increases have observed. Core has about 300 HV hardness, and this compound layer is having about 400 HV hardness. But this is not really the boroid layer, because boroid layer has a hardness typically greater than 1200 HV. So definitely that is not really the category of boroid, but its compound layer is forming initially. And here you can see that the sawtooth morphology is actually emerging in this compound layer. And as you keep on increasing the time you keep on increasing the bigger container where potential is also high, you can get the well-grown FEB layer as well as Fe2B layer. That means your container size and the amount of powder which is there with respect to the surface area of your material component is also very vital in governing the kinetics of your process. Okay, so that is also we need to understand. And here is another interesting thing. In case of a medium container, we are not seeing any kind of the FEB layer formation. You can see in XRD figure, that figure number A, and here you will not see any kind of the peaks corresponding to FEB layer. That means if your potential is controlled appropriately, you can avoid the formation of FEB layer. However, if your potential is high, that is the situation in case of the large container, there you can see the clear indication of the FEB layer, which is observed in SEM as well as in XRD. And there is interesting thing, that is a transition zone, which has formed between the boroid layer and as well as the steel matrix. And you look at the micro-hardness profile, so the transition region has a lower hardness. And that will happen at a later stage of the boronizing process. And what exactly this transition zone, we are very curious to understand, and we did some investigation there, and we realized that this transition region is basically associated with the enriched elements which are rejected by the boroid. And that particular is forming a undesired compounds in the transition region. And because of that, that particular region has a different property than the matrix as well as a compound layer. And in this case, we have observed its enrichment with respect to carbon, and as well as we have indication of boron there. That means there is a possibility of formation of a cementite, or the borocementite can be there. And because of that, the properties are different compared to that of a matrix as well as the boronized layer. So now the basic mechanism is very clear to understand for us, and this is what actually I already explained. And the transition zone, nature of a transition zone, what is that? That is basically rejected element. And in this case, we observe the carbon. However, there is other elements are also there. And at that time, in 2014, this paper was published. And at that time, we were unable to have much characterization there. So we are unable to understand this particular concept more into detail. Then later on, we focused more to understand this. And we selected the another category of the low alloy steel, that is the EN41B steel. And we did experiments at various temperature and as well as the durations. And then we subsequently investigate this. Now, in this case, optical micrograph, you can see the interesting phenomena. All are taken at the same magnification, that is except figure B. And all are actually exposed to 4 hours of boronizing. Only temperature is different. And if you notice, at a low temperature of 850 degrees Celsius, the boroid morphology, if you compare that figure number B, that is amplified view of figure A, and you compare with the figure D, you can see that there is a significant difference in their appearance. In case of figure B, it is the boroids are very thin in nature and they're very sharp in appearance. However, yeah, at very high temperature, that is 1050 degrees Celsius, these borides are not really very sharp. Their blunted tips are there. And if you go to the lower temperature, 950 degrees Celsius, the tips are very sharp again. That means you have the boride morphology significantly dependent on temperature. And this particular phenomena, and you can also see surrounding to the boride, you have some kind of a different contrast is there, which is appearing different than the matrix. And why that contrast is there? That is because of the different chemistry of that particular region. And we call this particular region as a matrix. So we have used the word boride columns, then we have used the matrix word, then we have used the transition zone region, and then we have a core region. So these terminologies we have used in this particular case. So now, before delaying much, so I will just go to this particular hardness depth profile. You can see that the hardness depth profile is significantly lower for the case of 850 degrees Celsius compared to that of your 1050 degrees Celsius. You may be wondering, because in case of 850 degrees Celsius and 1050, both the cases we are getting the iron boride. That means the compound there, but why properties are different? Actually, if you notice carefully, so there are, if you see that very high magnification region, there are open gaps are there, especially look at the figure number B. And these open gaps are nothing but the matrix. That means that region has not been transformed to boride yet. Even you can see that this matrix is there even up to the surface, even up to the surface. That means you have still trapped region, there is a matrix region, which is unable to transform into boride entirely. And this situation is aggravated, or the proportion of matrix is aggravated at a lower temperature. That's why whenever we take an indentation, you're getting the information from boride as well as from the matrix. That's why you're getting very lower hardness or least hardness at 850 degrees Celsius. However, at elevated temperatures, this region, the matrix region, is entirely occupied or consumed by the boride. That means that region will have only boride region. So that's why during micro hardness measurement, you're getting information only from the boride. That's why your hardness is very high there. Okay, so that means in principle, bottom line is that you have, in principle, you have the mixture of the boride as well as matrix. And we use the fraction of boride and fraction of matrix, that is equal to 1. That simple concept we have adopted here from this particular slide. And this transition zone, we use the word, wherever in transition zone, you can see very tiny boride particles. You can see in this micrograph. These tiny boride particles are forming, and they're forming along the grain boundaries as well as in the matrix, along the matrix. In principle, to understand the mechanism of the process, we have to understand this diagram in opposite sequence. That means core to surface. So why that is so? Because initially we have a non-boronized material. As you go further, there is a formation of a tiny borides there. Most likely the tiny borides will form at the grain boundaries there, and then they will grow in a particular direction there and form the columns. That means your mechanism is something, is this figure itself is telling us the mechanism, how situation could have occurred. So you just imagine the process from the core to surface. So in next sequence also, I will imagine this in opposite sequence. Okay, whenever I show the chemistry of this region, so there also we are imagining from opposite sequence. Now here you can see just enlarged view here. You can see that this basically the bigger size boride columns, they are formed by clustering the thin boride columns, which are happening during the growth process. And you can have still some trapped region, which is the matrix region is there. And you have also the formation of a defects, especially near to the surface region. And these defects are mostly the porosities. Now the EBSD, that is the electron backscatter diffraction, that actually helps us to understand the orientation of phases and as well as the what phases which are forming there. And we have confirmed that basically you have the stacking of 100 and 110 plane in a direction of 001 crystallographic direction. So that is pretty well confirmed here. And apart from that, you can see this particular region, you can see that near the surface, you have very fine grains are visible here. And then subsequently, there are columnar grains are visible. That means in this particular region, you have the two important regions in boride region, that is the small grains and the columnar grains. And then subsequently, we have a transition zone there, and then you have a core there. And why that fine grains are forming there? Most likely, whatever the matrix which is left between the two boride columns, they are transformed at a later stage into a tiny boride, but they are unable to grow because they are already restricted by the well-grown boride columns. So that's why they will remain in a very finer grains there. Okay, now we did a EPMA analysis that I will not go into the mechanism of EPMA, that you're already aware of that EPMA. And this is basically the chemistry. To understand the chemistry of these boride columns, we did the analysis point by point within the boride column and as well as in the matrix. And here you can see some of the interesting thing that we have very high boron content, which is already reflected here. And you can see some of the elements, like for example, silicon. that silicon content is almost like a 0. That means in boride region, it's almost 0. That means solubility of silicon is 0 in this boride column. And if you look at the aluminum in the next figure, so there also you can see that in boride region, this aluminum is also close to the 0. That means there is no solubility at all for the aluminum as well as silicon. However, the other elements like chromium and as well as the manganese, even moly, nickel, they have some solubility in boride, but that solubility is not same as that of your matrix. That means during the growth of boride, elements will be rejected. That is for sure. All elements will be rejected. Some elements will be accommodated into the iron boride. However, some elements are entirely rejected. Some elements like aluminum, silicon, carbon, these elements are entirely rejected. However, other elements will be accommodated to some extent, but some portion is also rejected. Now, this rejection kinetics or the rate at which these elements are rejected, that will be different for different element. And that's why near to the boride column, so you can see the elemental mapping here. And if you look at the figure number B, it clearly shows that we have the high boron region, that is the boride column is there. And you just compare with the figure number D, where this boride region is appearing dark. That means there is no presence of aluminum there. However, between the matrix, you can clearly see very high, that is a blue colored region is there. That means we have the presence of aluminum or segregation of aluminum is there in the surrounding matrix. But you go to the transition zone and matrix, you again it appearing dark. That means this region, the matrix region is enriched with the aluminum. That is because it's a rejection by the boride, and as well as the migration kinetics of aluminum is not great. And because of that, it is remained there. Because we're not seen any kind of such type of accumulation for the case of chromium as well as the molybdenum, even in case of a nickel also. That is why, because they are having a faster migration kinetics compared to that of aluminum. But in case of a silicon and aluminum, we have such type of issue of segregation is there. And this segregation or this accumulation restricts the boride growth or the thickening of this boride growth. That is also we have observed. And for that purpose, we have investigated the glow discharge optical emission spectroscopy, that is the GDOS. So I will not go into detail because this is very complicated analysis we did with this. Only thing what actually I want to mention in this particular case is that, so here the left-hand side image is for 950 degrees Celsius, and the right-hand side result is for 850 degrees Celsius. Both are at a constant duration boronized. And here you can see that this entire region is divided into different zones. And if you compare this actually nature of these zones are appearing more or less same. That means it's not just by accidentally we have got this particular profile. A system is really following some kind of a mechanism here. And that mechanism is a consistent. Even I will show you the different durations. There also it is following a similar trend. That means something is happening with respect to the migration of the element and the growth of this particular boride. And that is we need to understand. For that purpose, what we did is that we took a slope of this particular profile. And we want to understand how the slope varies. And here is the actually the slope variation. Here you can see that for the boron profile, you just look from the V to I. That means from core to surface. So there is a decrease in the slope is happening, and then again that is migrating toward the zero slope. That tendency is there, and that tendency is aggravated at elevated temperature. That is 950 degrees Celsius. That means what is the zero slope? Zero slope is means that there is a stagnation of that boride column has occurred there. It is unable to grow further. And why that stagnation is there? That is because of the accumulation. If you compare that the boundary line between zone 3 and zone 5 with respect to the aluminum and silicon, you realize that you have something is associated with the aluminum and silicon segregation in the matrix. And that also we confirmed in this particular analysis. And for that purpose, we took a mathematical interpretation. What simple interpretation it says? You have a total concentration. The total concentration of an element at any depth is basically a combination of the chemistry of the boride as well as chemistry of the matrix, along with the fraction of boride and fraction of the matrix. Simple lever rule has been applied here. And we interpreted this particular phenomena, and what actually outcome of this interpretation? During the boride growth, what happens? There are two types of categories of element. Some of the elements, they are entirely rejected. I will call them as a set number 2. And the elements which are accommodated into the boride, I call that as a set number 1. So set 1 elements. So set 1 elements are basically this concentration of these elements are in the matrix is not changing with respect to the growth. However, the elements, set number 2 elements, their concentration is increasing in the matrix as the boroding happens. Okay, so that is what actually the final outcome of this analysis. Okay, and the temperature wise, you can see that the temperature, what is the effect of that? You can see the transition zone becomes quite wide here. In case of the 1050 degrees Celsius, transition zone is almost 50% of your entire boride layer thickness. And this transition zone tendency is same as that of the slope is actually approaching towards the zero. That means you have some stagnation there, and this stagnation is linked with the accumulation of aluminum and silicon in the matrix, which you want to avoid. And that is happening because slow migration kinetics. And we did the different duration study, and then finally we did a kinetic study there. And then finally we have proposed the rate of the boride migration and as well as the migration of other element. So what actually you're seeing here, so you can see that this horizontal dashed line in figure C, it is related to the boride migration. So boride migration is more or less same as that of a migration kinetics of elements like chromium, nickel, manganese. Nickel is slightly less and very severe for the aluminum and silicon. So migration kinetic of aluminum and silicon is extremely low. And in case of aluminum and silicon, you have two types of migration. One migration is in front of the boride, sawtooth boride, and one is between the borides. That means in the matrix. And the morphology or the migration kinetics in front of the boride is still less severe. It is able to migrate at a fast rate. However, which is the elements which are accumulated between the boride columns, they are unable to migrate at a faster rate. And that is causing the restriction in the growth of this boride layer laterally. Okay, so now we have refined our understanding with respect to the mechanism, and we have proposed the matured mechanism here. And what actually we mentioned, we have correlated the migration of the element and as well as the nucleation and growth of this boride. And you can see figure number A to E, how the actually this particular phenomenon is happening during boronizing. Initially at the grain boundary, there is the boride formation, and there is a growth of this happens in a columnar fashion. And during that case, rejection of element happens. It will change the chemistry of a matrix. So you can see some kind of a grayish region here compared to that of the non-core, that is a non-boronized core here. And then finally, you have the simultaneous growth of transition zone as well as the boride columns. Okay, that is where how the layer actually matures. Okay, so now just how much time I'm having. So depending upon that, I will decide what rate I have to finish.
Yeah,
how much time I can?
10 more minutes.
Oh, yeah, sure. Thank you. Okay, so now we need to understand the properties. And this for properties, we recently did very investigation by using the nanomechanical study there. And nanomechanical, why we adopted the nanomechanical? Because in case of a nanomechanical, we can do a localized understanding of the properties, because that ultimately is crucial because let us say your boronized component is subjected to the wear. So whenever the wear happens, material loss will be there. Material loss will be there. That means your fresh material will be exposed. The fresh material will be exposed. That means your properties of that region is entirely different than the previous situation. That means we need to understand the local distribution of these particular different phases and their chemistry, how that is playing a role in understanding the localized mechanical properties. And for that purpose, we did a nano indentation study. And what actually we observed is that borides are definitely harder. That is well not reflected here in the table here. And the modulus of this boride is basically high. That is obviously expected here. And as compared to that of a matrix, matrix means surrounding to the boride. And we have the core region. That is the non-boronized core region. So here what actually we see that the E value, that is the modulus of elasticity, is definitely high for the boride. That is obvious here. Now the question arises, if the material is very stiff, there is a possibility of cracking during their growth. Fortunately, if you look at the another column here, that is H by E. This H by E basically gives us the information about the elastic strain. Even the HF by H max, that also is linked with that. And you can see here that the elastic strain, that is a H by E ratio, that elastic strain is a very high compared to that of a matrix and even compared to that of a core. That means even though that boride is a stiffer, but still that has a capability to absorb any kind of a lattice mismatch is there, which can absorb elastically there. That's why if you look at the adhesion test, that adhesion test confirm that this boride is quite having very good adhesion. So that means there is no issue of the crushing of this boride or detachment of this boride during application. That is unlikely to happen. So that is the best information we got this. And the matrix has definitely different property. That is because of the segregation of element. That means whenever you have the loss of material will happen and fresh material exposed to the surface, your surface is having the boride as well as a matrix, which has a different properties. They will have a different properties, and the properties of a matrix are different than the matrix, even though they appear like the boride free region, but their properties will be different because of the segregation of the element. That means depending upon the chemistry of your alloy, you will have a different properties of this matrix, and the response during application will also be different. Now, another information by what we can get from the nano indentation is basically the strain rate sensitivity. It is a very crucial factor. And strain rate sensitivity, what you can look into the bar figure in figure number F. And here you can see that basically which one, that M value, that is a blue one. And here you can see that this basically strain rate sensitivity is the highest, that means even higher than the matrix and the core. That is a good information. Why? Because how that strain rate sensitivity is useful for us. During application, we may have a different sliding speed. Maybe in cases sliding speed is slow, in cases sliding speed is faster. That means your strain rate sensitivity, higher is the strain rate sensitivity, there is a possibility that your rise in the hardness due to the strain hardening phenomena will be there. And that is actually helps us to improve the wear resistance. And that is actually we have also observed during our wear study at a different sliding speed. So that high strain rate sensitivity of the boride is advantageous in the case of especially tribological application. Now we also studied the oxidation resistance, and for the oxidation resistance, we removed the layer by layer. Purpose we understood because we want to see how the after deterioration of the surface, how the fresh surface will react with the ambient temperature. And for that purpose, we removed the layer by layer, and we took the XPS, that is X-ray photoelectron spectroscopy. And this XPS actually gives us the chemical information of the element at a different surface. And that actually helps us to understand how the oxidation response has occurred there. So I will not explain this more into detail, just simply explain the last figure on the right hand side, the bottom one. So here you can see that this relative distribution of element is mentioned here. What actually it says, as we are moving interior to the material, that means we have removed more and more layer, that is from D1 to D5. So what you are seeing here, as you are going inside, you have more and more fraction of matrix will be there. And more fraction of matrix will be there, that is reflected in a reduction in the relative boron content. Your oxygen level at the surface increases. That means your more and more oxides are forming at the surface because of less quantity of boride. That is obvious because iron is already bounded with boron near the surface. So less iron is available in the matrix to react with the oxygen. So that's why we have less oxides will be there at the surface. But as you go interior, you have the more and more oxidation happens. That means boride is having a very good resistance to the oxidation, even at a room temperature. That is a confirmed from this. Now there is another important observation, which is difficult to understand in generally, but XPS gives us the information. You can see the intermediate layer, that is a D3, you have very high chromium there. And that high chromium is because of the accumulation of chromium in the boride phase. And that accumulation of chromium in the boride phase is associated with the least or the lowest oxygen. What does that mean? That means that higher is the chromium content in the boride, your oxidation resistance will be superior. That means your composition of the steel is also playing a role in governing the resistance to the ambient atmosphere. So that means the composition is very important, especially with respect to the migration behavior. That means you have migration of behavior due to the accumulation into the matrix as well as into the boride phase. And here in this case, the chromium presence in the boride is helping us to resist the oxidizing environment at ambient temperature. Now at a elevated temperature also, excellent result we have observed. You can see here the red one, left hand side, the red one is basically the TJ result for the boride surface, and the blue one, the square dot, is for the non-boronized. You can see that is always lower side compared to that of the blue one. That means you have very good oxidation resistance is there for the boronized surface. Now, why that is so? We have observed by using the Raman spectroscopy, we have studied this composition, and we realized that during the oxidation, basically there is a formation of various oxides happens. And some of the boron oxides, they're having a lower melting point. So because of the lower melting point, these oxides will spread and cover the entire surface. And that oxide, that iron boron oxide, which is shown in the XRD pattern, and these oxides are uniformly covering the surface. And it is basically helping to avoid the further oxidation at elevated temperature. That is the mechanism basically helping us. However, at 200 degrees Celsius, you can see some erratic behavior. And this erratic behavior is linked with the porosities which are formed at the surface. That means we need to address the bad quality surface, especially which happens in the case of a boronite. So that is a challenge which is there, especially for the lower temperatures. So now the tribological behavior. So tribological behavior, we did the extensive study, and we compared the boronized surface with the normalized as well as a hardened and tempered as well as a nitrided. And then we also do a subsequent coating also there. And our counter surface was different. Initially, we use the hardened ASI 4140 disc as well as alumina ball as well as the DLC coated. That means wide range of combinations we have studied to prove that how boronized will be useful. And before I go further, I will just quickly give an adhesion test. So it is a very simple test by using VDI 3198 test. You can actually determine the adhesion, and they have some different scales are there. They are mentioned from HF1 to HF6. Generally, HF5 and 6 are not desired. Up to HF4, it is acceptable. And in case of a boronized surface, you can see it is lying on the HF3. Now, if you deposit a coating like a DLC coating on the surface under the same load, you can see that your adhesion is further improved. That means, in principle, very thin layer of deposition of DLC layer can be useful, especially to avoid any kind of a cracking during the interaction during application. Okay, so that is beneficial here. So in principle, you have very good adhesion for the boronized layer, and it can be further improved by using the coating. And here is this bar graph clearly shows it is performing very well boronized surface compared to that of a normalized and heat treated condition. And even if you see the right hand side graph, so there also you can see the coefficient of friction is also very low, extremely low compared to that of normalized and hardened tempered. However, that is not really can be called as extremely low because it is still about 0.5 something. It is not really, we are not really happy with this coefficient of friction. 0.5 is a really very high value. That means we are getting a very good improvement with respect to loss of material, but coefficient of friction is not really great. And for that purpose, we need to see the effect of DLC coating. And that was our motivation to go with the DLC coating. And it actually helps us. Okay, so now I will, before, due to lack of time, I'll just quickly run through that and I will just give you the information which is crucial here. So I mentioned that we did the boronizing or wear loss study at a different sliding speed. And you can see that particular table, you can see that the wear volume, which is conducted for 0.5 meter per second sliding speed with respect to 0.3 meter per second sliding speed. You can see that this ratio is less than 1. That means at a higher speed, your material is performing very well. And this effect is, or the gap between this, their wear behavior is keep on increasing as you keep on increasing the load. That means, in fact, your material is behaving very well at a very high speed compared to that of the lower speed. And that is probably linked with the SRS. It is a strain rate sensitivity. That is what actually we expect. Obviously, so the top graph is not really giving us the good information about boronized surface. What it says that initially the difference between the boronized volume with respect to the non-boronized surface, you will actually lose the advantage associated with the hard surface as you keep on rising the load. But still, here you can see that at very low load, boronized surface is behaving extremely well. Your difference between the wear volume for the non-boronized versus the boronized is about 45 times. It is better. However, it is at higher load. It is about only 10 times better improvement you will see with the boronized surface. But still, that 10 times is not really bad value. So it's really good in that regard. Okay. So now, as I mentioned, coefficient friction is still very high, 0.4 to 0.5. So it's not really good. And this wear mechanism we studied, and mostly what happens the wear, mostly it is a cracking and the oxidation. These two phenomena are actually dominating, and that is actually causing the loss of material generally. And there is during sliding, there is oxidation of surface occurs, and that oxidation is debris are actually causing the further wear of the boronized surface. Now the DLC coating I will just show here. So either of the surface is a DLC coated, that means in a counter surface and or the boronized surface. In that case, your wear performance is extremely good. Even at a high load as a 100 Newton or 150 Newton, it performs very well. Because what happens, because of the DLC coating, and your coefficient of friction is also very, very low compared to that of your earlier. You can see the value is 0.09 or even close to 0.1. It's an extremely good value you can get by using the DLC coating. So what is the reason? Basically, there is as you keep on applying the load, there is a formation of a transfer layer. It is a graphitized layer, and that graphitized layer is helping to help in reducing the wear loss as well as to reduce the coefficient of friction. That is the basic mechanism which is happening because of DLC coating. So this same thing actually we are actually mentioned, and here you can see that in fact your performance keep on improving as you keep on rising the load. That is the beauty of DLC coating, because as you keep on rising the load, you have more and more transfer film, that is a carbonaceous film, which is forming at the interface, and that is actually helping us to improve the property. Okay, and here this comparison with respect to your nitrated sample as well as a normalized sample, you can see that AB pin, that is as boronized surface against the DLC coated D2 steel, it is extremely well, extremely good behavior has observed, especially for this particular situation. That means if you are using a DLC coating, better not to polish your boronized surface, better to have some roughness there. That roughness is helping us to accumulate the transfer layer, and that actually helpful advantages. So better not to polish the boronized surface. So that is actually this particular slide helps us to understand. Okay, so summary point of view, the microstructure. So boronized region consists of the iron boride, and this iron boride consists of not only iron, but as well as the elements which are having some solubility there, like chromium, manganese, moly, nickel. That means we have some kind of a mixed boride is forming there. And then in that particular boride region, you can have a fine grains at the surface and columnar grains. Then there is a subsequently followed by transition zone. Transition zone consists of very tiny boride particles are there, and then subsequently non-boronized core. And the solubility of elements like carbon, aluminum, silicon is extremely zero in iron boride. That means they are entirely rejected. And the morphology of this iron boride is very much dependent on process parameter like a temperature and the kinetics of migration kinetics of this element. That is what actually we have seen here. So because of that, your chemistry of your matrix, it will be entirely different during the growth of boronizing because of accumulation of certain elements there. And the initial study, what actually mentioned, it mentions that your preconditioning of container is desired here, and generally better to avoid the formation of FEB at the top, because that is not really advantageous. It will probably crush and it will be get detached from the Fe2B layer. So that is better to avoid that as much as possible. And then with respect to property, extremely good hardness you can get. Depending upon the proportion of ferrite and matrix, your hardness can be as low as 1200, even as high as even 2000 HV is there. And even the non-ferrous material can also give you the porites there, and it can give you even further high hardness there. And the superior erosion and abrasion wear resistance has observed. Galling resistance is also extremely good. And deterioration is of this boride is quite less, even at high temperature, due to the good oxidation resistance, and the corrosion resistance at the ambient environment, especially alkaline and acidic media, is also extremely good on the basis of our work as well as from the literature. And applicability, that wide range of materials can be used boronized by using this technique. And DLC will be quite useful to get rid of some of the disadvantages associated with the boronizing. So that is what actually the summary of this. So there are plenty of literatures which are available there. So there is always be plenty of things are available. Yeah, thank you.
Thank you very much, Doctor. So, any questions here? We can take few, though it is a bit late, but we can still take few questions.
I would like to ask a question, if I may.
Yeah.
Now we have heard just now that boronizing has given gives so much advantage to the steel. Then why is it that it is a very fairly old technique? It is not that it's something which got discovered recently. So why is it not very popular?
I am not really sure about this. So probably the pack system, probably people are consistency of the result probably could be an issue early days, but nowadays people have extensively come up with the ready-made mixtures, and which was not there earlier. For example, that the German powder, what I mentioned initially, that Icabor, and that actually gives that promising composition of that particular powder. That means there is a claim that you can get very consistent result there. Probably the consistency of result, probably one of the reason for this particular case. And another reason could be that gaseous system was not really extensively studied, and probably that is another reason. Unfortunately, in case of boronizing, the limited information is there. However, in case of a nitriding, the gaseous system or plasma-based systems are well established, and it is easy or handy to operate. And another thing is that the nitriding can be there at a lower temperature, even less than 600 is possible. But in case of a boronizing, we have an issue there. Issue is especially with respect to the reactions which are happening there, especially for the boride formation. So that is another disadvantage with respect to the nitriding. So that's why probably it is not that popular. However, definitely this can be the alternative to the carbonizing process, because carbonizing is done at elevated temperature and boronizing also generally done at elevated temperature. And definitely here we are getting the very good property with respect to the typology and as well as other mechanical properties. So yeah, so I'm seeing that. So that's why if you see the recent days, people have, I'm getting more and more publication in this particular area. And companies I have seen from USA, they are also successfully doing this particular treatment, that boronizing of various components successfully, which was not there earlier. So that means now people are realizing the importance. That is what actually I believe.
One question from my side, doctor. You spoke about boronizing of steel and utilization of that into our farm equipments and farm implements, right?
Right.
Because where resistance requirement is very high.
Right.
So why that is not been extended? I mean, I don't know of any this thing where we are using such boronizing for improving wear resistance for farm implements. So do you know of any this thing and how that can be of help to industry?
As far as my understanding of literature, so people are actually using this technology for the farm equipment. In fact, that vapor coat, that company, they are doing this. So I'm not sure why that is not really popular in other part of, especially in India, why that is not there. But as far as my understanding, it will be definitely useful and it is worth trying. If really industry is having a doubt on this technology, we definitely have some component and we can do some field test. And that field testing will give you the more confidence, because as far as my understanding, the companies from USA, they have already claiming that it is quite advantageous, not only from a tribology point of view, but as well as a corrosion point of view, especially the range of the soils which are using.
Yeah, doctor, which company did you mention? Vapor?
That vapor coat, if I remember, yeah, that vapor coat is there. So
anyway,
yeah,
I
just
will have a different discussion with you on this. So till such time, yeah, I'll connect with you on this. So
yeah, we
let's see.
just check.
Yeah. No, it's okay. We
Yeah,
can
it is
do it later on also.
Yeah, its vapor coat is there, and as well as a blue water thermal solution. Vapor coat and blue water thermal solution. So these companies are actually claiming. So even for oil well tubing, even the drilling tools, so that is quite popularly applied. Even they tried with the nickel-based superalloy also. So nickel-based superalloy also is possible to be boronized. We work a little bit on that area, and we also observed some improvement. Nickel borides are forming there.
Dr. Santosh?
Yeah.
I have a couple of questions. Firstly, I would like to thank you for a very interesting topic, having been selected for your research. And
thank you.
I thank also our ASM group for having selected you for this particular presentation. It really is quite interesting. And I have a couple of questions. You 2-3 times mentioned that it is also being used for non-ferrous materials. Can you tell me which specific alloy system or material you have used?
Yeah.
It is used.
Yeah, actually what I have observed is that there are plenty of literature which is available in two important material. One is the titanium and as well as a nickel base. So nickel based alloys are successfully done. Even the cobalt based alloys are also successfully done. So cobalt based alloys as well as the nickel based alloys and titanium based alloys. So they are successfully boronized by using this technology. Because there is a formation of chemistry wise, they have a reactivity with the boron, nickel as well as the cobalt as well as the titanium. So titanium borides and nickel borides, so they're actually forming. And that's why it is successfully done.
My second question is regarding this heat treatment cycle that you indicated. You are heating it to about 850 to 1100 degrees centigrade, in that range.
Right.
Right. In that, actually boron is getting diffused. And we are forming either FeB or maybe Fe2B. FeB2B is supposed to be more advantageous. But Is it
Right.
subsequent to that? Are you quenching it in some quenchant?
Yeah, actually, we tried initially with quenching as well as the furnace cooling and as well as the air cooling. And what I observed is that there will not be much different. In fact, we realized that quenching is not really recommended because quenching will, there is a possibility of cracking is there. However, you can easily go with the normal atmospheric cooling is there. That probably save the time. And in case of a furnace cooling, there is not much difference with respect to thickness of the borate. Because probably to decrease the temperature from 800 or 1100 to lower level where the reaction is impossible to occur. Probably during that duration, some of the reaction can lead to the rise in the thickness of that particular layer, which can occur during the furnace cooling. Otherwise, air cooling is a pretty good enough. Within probably a couple of hours, it will be cooled, and there is no difference with respect to kinetics. So that can be done.
I was wondering because you had selected both the system 4041, 4140 and EN41B. Both are in
Right.
that medium carbon.
Right.
So I was wondering if you quench it, what will happen to the core? Even that will tend to get hardened.
Exactly. So that is actually, we are not really focused much, but definitely that is interesting thing which we look around because initially we focused only about the boronized layer. That was our main motivation scientifically. But definitely for a practical application point of view, definitely we need to have the hardened and tempered core is required. So we need to understand what happens with the core, especially the quenching. So, but yeah, so let us, we need to study that. Yeah.
Professor, I have
Last question is, last question, sir. Last question is regarding the columnar structure of boride that you form.
Right.
That must be leading to subsequent brittle failures, you know.
That's what actually people generally expect. But what we observed is that it is not the case actually. And because you have the matrix, which is matrix is still sufficiently strong enough. Why that is so? Because whatever the elements which are present there, that actually helping to enhance the property of the matrix there. And as I mentioned, if you see the elasticity of that particular thing, that elasticity is a very good there. And because of that elasticity, we will not have that crushing type of a thing is not there. Even if we studied about the very, very high load, but still we're not seeing any kind of very crushing we generally observed in case of the nitrated compound layer, what we generally see. So that type of a thing is not there. That means their properties are entirely different. We should not look at this compound as the brittle material. It is associated, it's hard, that is true. But at the same time, it is having a sufficient elasticity. That is advantageous. I
am Sudhakar Bonde. I have a small query. This is regarding the testing part of it.
Right.
This corrosion testing is done on this component as to what ASTM specification basically?
Yeah. Because actually we have not studied the corrosion in our work. We have only studied the oxidation in our work by using XPS. But people are using the corrosion study by using the standard test method. That is as per the ASTM. Yeah.
Okay.
So people have done that and they have even showed the improved corrosion resistance. Yeah.
Okay.
So that is there. Yeah. In fact, not only just your normal NaCl solution, it is also useful even in some acidic media also. That is also plus point there. So,
Do you have some facility whereby we can do some trials?
Yeah, actually, I'm doing this boronizing at my lab only. But obviously that lab is, so small components we definitely try. Because of my furnace chamber is small. So that's why limitation on the size of the component. Otherwise, in principle, size should not be an issue at all.
You got patented or what? You got
no, sir. No, actually not the patented. So it's like a openly available. So that information is openly available. Only thing what actually I am very much fascinated as a metallurgist, that is especially the physical metallurgy is my interest. So basically whatever the redistribution of this alloying element happens, that is something we extensively proposed. And if you see, we published this paper just in 2020 and you can see the citation of that paper. Immediately it is almost like a 10 times or 9 to 10 times it's already cited. So that means people are actually looking into this particular scientifically. And another thing is that people are also started working in this area. So that is actually, it reflects. Obviously, I'm not saying that,
plasma and other techniques are also getting added to this methodology. and
Right.
should be able, we should be able to do it at a much lower temperature because of use of plasma.
Exactly. And that is what actually, if I remember, that Oak Ridge National Laboratory in USA, they're doing a plasma-based boronizing method. They're using a plasma-based boronizing method. So that's why they have a control over the temperature. Unfortunately, to get that particular setup, laboratory setup, so I will not get the funding from the funding agencies. So to get a plasma setup, and so that is the challenge. Otherwise, so in India, nobody is actually exploring that. I have that particular idea. In fact, my students who worked in this area, that Mr. Joshi and the Aditya, so they are also actually saying that we should work on plasma-based system that will give something additional information. But unfortunately, nobody is there who can actually help me to get a plasma system. But that will be interesting, definitely interesting. Yeah.
Dr. Santosh, one suggestion.
Yeah.
I don't know whether you have explored that. Our Gujarat member or Gujarat chapter chairman,
okay,
Dr. Nirav Jamnapara, is an important part of India, this Plasma Research Society.
Okay.
Plasma Research Institute.
At Gandhinagar. And they are into plasma nitrate. Possibly you can interact with him and explore the possibility of doing plasma boronizing.
Yeah, definitely. In fact, we interacted with the Plasma Research Institute for get a plasma nitrading initially. So I forgot the scientist name there. But the boronizing, I have not explored. Definitely, that will be interesting information. So I will interact with him.
A lot of people they are doing in plasma nitrading. I think that's in Pune also. There are some people.
Yeah,
yes. Plasma nitrading
right.
is very common these days. I think Avadhoot also does it in Pune. So that's
right.
The only thing is plasma boronizing, and you are making it helpful for industry. That could be the challenge. I think we will we will work something on this. Let me first understand from our R&D if they are doing anything on this. If they are not doing anything, and if they are very this thing, then I will definitely revert on it.
Yeah, definitely. I think a lot of potential is there, this technology, and plasma base will definitely useful, because I'm at a low temperature probably will get rid of this morphology related issues also. So that will be quite interesting, not only just scientific, but also technological point of view also.
There is one industry which is in Rajkot, which is Tirth technology. I mean Tirth automotives. They are using. They are into making farm implements, and almost they are selling it to 88 countries in the world. One of the biggest one in this thing, and they are also very into expansion and all. I have good contacts there. Let me see if I can do something about it.
Yeah, that will be useful, because somehow
I'll be in touch with you.
Yeah, definitely, sir. Definitely, that will be useful.
Thank you. It was very nice, doctor, about learning something which really can help.
Yes, sir. Because we have to. Because ultimately we have to find the alternatives to the conventional processes. So now the people are working. That means definitely there is some potential is there. So that is so we should realize.
Yeah,
so I think
explore that.
Yeah, right.
Yeah. So in if everybody is exhausted in their questions, maybe they can keep some questions for one-to-one reactions. I mean one-to-one interactions. So I would now try to would like to sum up. Dr. Santosh Hosmani, thank you very much for your interesting topic of boronizing. Actually, there are very less participants, but given this thing, we could have definitely made more this thing use for of your. We will try and do something definitely in the industry on this.
Right.
So thank you very much once again, and it was very nice to look at the systems of boronizing, effect of alloying elements in iron systems, like what you were talking about, this carbon, silicon, aluminum, which restricts the boronizing growth. That sawtooth morphology, and it is very interesting to note that it is with low alloy steels it goes very well. Otherwise, generally for high alloy steels everything goes well, but then this technology goes well with low alloy steels also. So the prices of industrial this thing usage can be of lesser this thing. So it will be very interesting if you could do it for industry. So
Right.
also the wind resistance, the DLC coating you talked about, the rough surface not to polish this thing. So that is also very nice. Also, we have it's very interesting to note that there are some industries which are using it in the world. You also talked about you started with your this solid this thing boronizing pack carbo like pack carborizing, it is pack boronizing, so powder pack boronizing. So that was very nice. Also very nice to hear that that boron source, boron activator, diluents, and that process temperature is also very notably between 850 to 1100. So that's also good. And really somebody has to work on this really to help us out into industrial usage of this. Thank you very much, doctor. And
Thank you, sir.
yeah, and we'll definitely be in touch with you. At least I myself will be in touch with you, and I think there are a lot of participants who have shown keen interest in the technology. So they will be also interested to know, be in touch with you and have good interactions. Thank you very much
Right.
for taking your time, and we also look forward to your help in our MET HTS 2021, like what Sabnish ji also talked about and Sudhakar ji also talked about. And definitely we will work together and on other platforms as well. And we would like to have another lecture of yours on some other topic. So we will have some more interactions, which will be good for the industry. Thank you very much,
Yes.
and thank you very much to all the participants who were there at this late hours. And good night to all. Good night, doctor.
Yeah, thank you. Thank you very much. Thank you very much. Thank for invitation here. So really I enjoyed. So definitely we can work together, because ultimately whatever we are doing in a laboratory, I'm keen to understand that in industrial scale, at least we should do some field study to really explore the potential of technology. So I think we should work together, so that will definitely benefit
Yeah,
to the community.
Will be one step forward towards Atmanirbhar Bharat.
Right, exactly. Exactly.
Okay. Bye.
Thank you. Thank you very much.
Thanks.
Thank you, sir. Thank you.
Thank you so much.
Good night.
Thanks. Bye.
Session now.
Good night.
Good night.
Good night.
Night. Good night.
Thank you.